So question 6 is from user GWM21, and it says, what is the most profound event you've ever correctly predicted in the past? That's actually a tough one. Certainly when you say I'm going to take it for a minute as, personally, I've been at this for over 30 years, actually closer to 35, in the sciences. Probably the single most profound event that we've predicted had to do with a very fundamental change in how silicon technology would progress in the future. In the early times of about the year 2000, 2001, 2002, 2003, we had already become aware of a very interesting transformation that would happen. You see, you probably have all heard of something called Moore's Law. And Gordon Moore, who's an absolute genius, one of the founders of Intel, correctly predicted a very interesting trend. He said basically the amount of stuff you put in a chip has to double or go up by, double roughly every 18 months or so. And this industry will progress just like wildfire. And he had that right, and that, by the way, has worked for about 40 years. But Gordon equally well understood one of the limits, which is, imagine you put twice as much on a chip and you do this for a period of 50 years. Well, if you've done nothing about the amount of power each thing you put on that chip burns, you have 1,000,000 times as many stuff on the same size chip. The problem is that if it used to burn 10 watts, it now burns 10 million watts, which in a laptop, when you turned it on, would provide you with a brief but incredibly exciting experience. Rather than set fire to the user, because Gordon is, as I said, quite brilliant, he knew better than this, a lot of people had obviously heard about this notion and worked on how do you avoid this. One of them was a very famous fellow named Bob Denard, who actually is one of the IBM fellows and who, for instance, invented memory, which you probably have all heard of. The fact is, Bob wrote a recipe, literally like the recipe cook rice. Well, this is the recipe for scaling transistors. And it's real simple. He wrote a recipe that says if you make this layer this small and that layer this small and you reduce things by certain ratios, what's going to happen is if the transistor is exactly half the size, it will burn exactly half the power. Perfect. You put twice as many things on the chip, they each burn half as much power. The next chip has twice as much on it, but it still burns the same power. So your 10-watt chip 50 years ago is still 10 watts. However, notice what I said along the way. You make things smaller. In fact, some of these layers you make half the size each time you do this. Anybody who's ever tried to fold a piece of paper in half 20 times understands that somewhere around the 7th or 8th time it becomes physically impossible. That's because you get too small, and guess what? Same thing happens in the real world. You actually make some of the layers in transistors small enough they start to get to the atomic scale. At the atomic scale, or near the atomic scale, bizarre new phenomena turn on that cause the device not to work. Okay. Unfortunately, a lot of folks missed this coming, and we correctly predicted this in the mid-90s and designed entire systems built around what we call multi-core devices. These were actually chips where instead of trying to make them run faster individually, you put multiple logic cores on a single chip, made for great systems. The world hadn't really caught on to this, and we actually finally went out publicly in the early 2001, 2002 timeframe, and I gave numerous talks predicting the end of what's called classical scaling. Don't confuse that with the end of Moore's Law. Moore's Law just says you put twice as much on things. Classical scaling is the recipe people followed for 40 years about how. The how changed. Instead of just making things smaller, we had to use entirely new materials for some parts of the transistor. And that was a profound shift that occurred, and now it's of course broadly accepted, but there was a lot of pushback early on because a lot of folks had been at it for so long they'd forgotten that classical scaling, how you make it smaller, is not the same thing as Moore's Law, which correctly predicts that you will make it smaller at a certain rate. So that was a profound shift we saw coming, and because I saw it coming, we acted upon it as an organization and really essentially weren't impacted by it. There is, however, a very logical follow-on in question 7. Question 7 from Insurance is Boring says, what is the solution to quantum tunneling with respect to current leakage in VLSI electronics? What do you foresee that replaces silicon-based chips? Now, this question is actually a perfect follow-on because, of course, it addresses the fact that now the material that's gotten too small to correctly scale, or will shortly, is silicon itself. Previously, things that were silicon dioxide insulators got too thin, and we went to new types of insulators. But the basic material of the transistor, when you get down to about 7 nanometers in a device, which give or take is something like 35 atoms worth of transistor, at that kind of dimension, silicon starts to demonstrate what are called quantum mechanical behaviors. So a classic transistor, if you just made it smaller at that point, ceases to work. The fact is you can go beyond those dimensions, but you can't build a classical transistor. They're called CMOS transistors nowadays, field effect transistors. Those don't scale any further. So that whole thing ends, which is really quite an amazing shift. At that point, you can either go to transistors that actually use these quantum effects in silicon. We call them quantum wires. We've demonstrated some of those. Or whole new materials, materials based on carbon nanotubes, materials based on, for instance, graphene. It's a single atomic layer, effectively, of carbon. If you take a pencil lead and you rub it across a sheet of paper, effectively some areas of what you've left there, that brown stuff, is graphene. And we've developed techniques to grow this on a wafer and actually made transistors on it. We just had a release a couple of weeks ago, in fact, at a conference, professional conference called IEDM, where in great detail we described such transistors. Very small carbon nanotube transistors, very small graphene transistors. So we are working on the follow-ons. By no means will IT stop. Information technology will continue, but this will drive a seminal consolidation of the industry to those who are working on these very advanced techniques to go beyond what right now at least are pretty tough-looking limits. We will get past this. IT will continue at the present rate and pace, but there will be a lot of different things we do in terms of new materials, perhaps stacking devices, which we already are engaged in, where you put actual stacks of transistors versus just horizontal arrays. Many different options are there. But this is a great question because this is another seminal shift that is yet to come. Question 8 is from user String97Bean. And it says, which of these do you feel will be the most important to the average technology user? And what they're referring to is which of the current predictions will be the most important. To the average current technology user, I think there's no question that the issue of biometrics being at least able to offer an alternative to password use will have profound implications. Again, you have to be very aware that there's good news and bad news, and we'll have to address all the aspects of privacy and the ability to essentially perhaps hold all the biometrics in a local device and not share them outside of that device. So you still remain anonymous, but your device knows with absolute certitude it is you with whom it is working. So there are a lot of issues to be dealt with, but from a foundational point of view, that is the number one in terms of a change people would see and immediately recognize. But that's the average technology user. To be clear, there's a second question, which is just from technology user in general. You're talking about the elimination of the digital divide, essentially having pervasive access across the world, with more than 80% of the world's population now having true access to the web and one another. That, just from a societal point of view, has also some profound implications. But the more visible, immediate, visceral one will be the one relating to passwords, at least in my opinion. The ninth question is from user GLR123. And it asks a very tough question, and it's a long one. There are about 8 questions in here, so I can't address them except at sort of the highest level. And just to net it out, what the user is asking is, how do you see the evolution of the work between governmental, university, and private industry-funded R&D? There's a very tough question there because you have to ask who funds what and how do you deal with it. I can't speak, for the nation or for the government. That, of course, is not my place, nor frankly do I have the knowledge. But I can speak from example, which is actually probably the most powerful thing I could do since it's reality. The example I'm going to give is go back 10, 15 years in New York State to SUNY Albany, State University of New York campus in Albany. And there was a small research center just starting to work on things like nanotechnology, a handful of researchers. That's all that was there. You go up there today, and the first thing you're going to notice is there's this enormous, ultra-high-tech campus with 30, 40, 50 different companies working there together in collaborative innovation, a whole ecosystem working on the very foundational limits of silicon technology. In fact, silicon technology, from the point of view of the Silicon Valley, where silicon is actually done and researched, is now in New York in the Hudson Valley in Albany. That is a huge transformation. And the reason it was successful, it was an incredible combination of wonderful government support, IBM placing huge bets, frankly, on the success of that area and actually investing extremely heavily. And similarly, us being very open to creating an ecosystem. It's really radical collaboration where we brought in folks from all over the world, many companies, companies from the US, such as Applied Materials Corporation that builds a lot of the equipment to do semis, folks like ASML from the Netherlands, who do the optics that enable you to actually define a small device. Folks like Tokyo Electron Limited that build a lot of tools on which you do semiconductor processing. They actually have consolidated their R&D efforts at this site, or at least are a participant at this site, because the best of the best are there. It's not the field of dreams. It's not if you build it, they will come. We built it, they came. It's a wonderful example of how the university has collaborated heavily, the government, IBM, and numerous others. I don't want to make this. It's not just about IBM. It's really a tremendous success. And of course, just more recently, Global Foundries, which used to be the manufacturer, spin-off of the manufacturing arm of AMD, is in fact building one of the world's largest semiconductor fabs on site just nearby so they can tap into that expertise. I mean, it's just one of these incredible virtuous cycles because we have figured out a good model for collaboration. So those models are viable and those models continue. And that sort of nets out, at least from personal experience, what I've seen go on and how that can be a very powerful force. And this is all, by the way, very recent, so by no means is this dribbled off into non-existence. This is a current example and is ongoing. Question 10 is from Dimsaduk, and it's interesting. It asks about hoverboards. Hoverboards, when? Well, now there's slightly outside my core area of expertise, but I've had kids. I've probably gotten the same question. The net of it is, interestingly enough, if you're willing to suspend disbelief just a little bit and go big, I mean go like really, really big, you got to fly to Shanghai, get off and take the maglev train into New Pudong from the airport. And as this thing floats on a magnetic levitation cushion and accelerates to above 400 kilometers per hour, it's quite an experience, and you're basically riding a levitating hoverboard. It just happens to weigh several hundred tons and be the size of a rather large train. Unfortunately, scaling that down to anything you're going to be able to deal with in the near term, I have no idea how you do that. But at least I can give you a macro example. So, basically you fly to Shanghai and use your imagination, and you can get a little piece of the experience. Not to mention, you can look out the window down at the highway beneath this and try to figure out how to get your mind to accept the fact there are trucks underneath you going backwards at 250 miles an hour. It's an interesting experience at many levels. So I'm going to wrap up there, but, as out there as the question, some of them seem to be, the truth is out there generally just takes a little longer. So I never write anything off. So that kind of wraps it up.